Hello, my name is Brandon Bailey, and I work at the Aerospace Corporation within the cybersecurity subdivision. And I'm here today to talk about some research we've been doing on trying to figure out how to unbox the black box that Spacecraft software is starting to become, looking for weaknesses and vulnerabilities in this software. There's a couple of links to some papers that have been published in the last couple of years related to cybersecurity for space systems. If you are interested in learning more about that topic, please give those a read. So let's jump right into it. So the problem that we're really running into right now, and the driver for the research is we're having a commercialization of space that's kind of expanding the usage of open source and third-party software within our spacecraft architectures. And in the past, we were operating with more of a white box mentality, and we had full source code access at times. And now we're moving into this black box realm where we're not really sure all the components that make up our spacecraft software. And it really makes it difficult for software assurance providers. And so we're trying to figure out how do we tackle this problem moving forward as we are getting more and more black box software to perform mission critical activities. So we perform some research to identify tools and techniques on the market or open source that could help evaluate the security posture of software without the presence of source code. And that is a key element of this. And we also wanted to kind of tailor the research as much as possible to hardware architectures that will be typically seen on common spacecraft. So that could be your PowerPC, ARM, Spark, and those type of architectures. So we wanted to figure out, could we automate this code inspection mechanisms in a cost-effective, fast, and repeatable manner? Could we look into, even if we had the source code, maybe assess the quality as the as-built flown components? So, because sometimes you may get compilers that put in weaknesses. And we did focus on embedded applications and embedded architectures, but we did look into some of the more standard x86, 64 binaries, because that is a problem area as well, especially for ground systems. The ground system flights, the ground system software that we are working with these days is also becoming somewhat of a black box. So we wanted to not leave that out, but really did want to focus on the embedded side. And as stated earlier, we wanted to look into the integrity of the build process and see if there's any vulnerabilities that were introduced by compilers. So essentially, the goal was performing software assurance of spacecraft binaries without having access to source code. And while we were doing that, we did get to tinker around a little bit with if we did find some weaknesses and vulnerabilities in the software, could we bridge the gap into exploitation? So we'll talk about that as well. So what is software assurance, and specifically software assurance when you deal with security assurance? So in our opinion, it has 5 major technical analysis approaches to help reduce the risk of vulnerabilities and software risk. So pretty much a standard practice in today's world is when you have source code, you perform static code analysis for looking for the exposures of common weakness enumerations or CWEs. You're looking for best practice adherences. You're looking for coding standards, violations, code complexity, code functionality, those type of tests. It's less standard for binary. And also for a security assurance, you may look into the kind of the vulnerability analysis, which would be kind of identifying the known knowns. So those will be your common vulnerabilities and exposures. So that would be CVEs, or maybe if you're in the government, you're assessing some sort of STIG compliance or CIS benchmark. Something that's becoming standard in the software assurance community that is long overdue is probably the dynamic analysis, dynamic testing of the software, trying to break it while it's under execution. So that could come in the form of penetration testing, that could come in the form of fuzzing. It's been pretty standard for the most part from a functionality-based perspective. We have a pretty good testing program for functionality-based testing, but you're starting to see the expansion of this into the security realm and doing fuzzing and doing red team type activities and pen test type activities against these software binaries. And something to note is with the spacecraft specifically and in the embedded architectures, advancements with digital twin technology in the last 10 years has really allowed for some of this dynamic testing to occur. So that would be your being able to use instruction set simulation to build out simulators that you can run these embedded binaries without having the hardware present. So another thing that's becoming standard that is not quite adopted across the community quite yet is like your software bill of materials, SBOM, software composition origin analysis to help identify the components within your software, and looking for CVEs as well as any open source licenses that may put you at risk. So this is the kind of the 5 areas where I would break down software security assurance. So I'm not saying this binary analysis technique that we're going to discuss is the only solution for software security assurance, but I am saying it's a key component, or can be a key component, especially when we don't have source code. So we're going to dive right into the binary. So the binary analysis, static code analysis is where you typically find some of your CWEs. This origin analysis or software composition analysis and vulnerability analysis will help find your compliance and your CVEs, and your 0-day discoveries will be more in the dynamic analysis of fuzzing. So 4 of the 5 are pretty well researched, and binary analysis is becoming well researched, but it's not quite, you know, as widespread known on the embedded side. So that's what we're going to focus on, the embedded aspect, and not so much on the Windows and Linux aspects of it. So when you talk about binary analysis, what do you actually mean? So I've met with vendors, I've spoken with a multitude of analysts in the last few years, and it can mean a lot of things to a lot of different people. So we're going to define what we mean by binary analysis for this presentation. So some people say binary analysis is really composition analysis, which there's an aspect of that is true, or origin analysis is often referred to. So that's not what we're talking about. Some people would refer to binary analysis as behavior analytics. So that'd be kind of like the more malware focused analysis with sandboxing, you know, your Cuckoo sandbox and those type of things, where you would do behavior analytics on a binary to determine kind of what it is. And that would be like requiring an execution environment. And then there's the dynamic execution. Some people would say binary analysis would include binary execution, which has some merit, but that's not exactly what we're talking about. Some people would say binary analysis has some fuzzing components, which it could be true, but you know, and others would say when you say binary analysis, a lot of people jump straight to this mindset, which is typically where I was before performing this research. So I would assume if you're doing binary analysis, you have a debugger, you have a disassembler, you're reverse engineering the binary, you're loading it up in a product like Gidja or IDA-Pro and really decomposing the binary and going through it. Problem is that's very labor intensive and very specialized skill set. So what we're looking for are things that kind of are synonymous to what we would once call static code analysis. That would be scalable tool sets that can do binary analysis across a multitude of binaries and pull out potential weaknesses that we can look for false positives and things like that. So that's kind of what we're looking for through this research, and that's what we'll talk about. So correlated to the list on the previous slide, this is a sampling. It's not you know, an exhaustive list across the board, but these are some of the things that we looked into as it relates to binary analysis and what our focus area was. So our focus area was down here in the bottom left. So this was looking at COTS applications that do the quote unquote binary static analysis. We looked at the free and open source software that does that. We looked at a little bit on the reverse engineering disassembler area, because those can be used as extra tool sets once you get the results from the binary static code analysis. And then we looked into a little bit on the dynamic execution side, like how easy would that be without source code access, and how beneficial it could be, but it could be extremely time consuming if you don't have insight into the binary like the source access. We looked into fuzzing as well, but fuzzing is not very mature on the embedded platforms from a BlackBox perspective. So that's kind of what we're going to focus on. So if you're to arrange kind of what we've discussed on a tiered pyramid here, I would view things as like, this is kind of like static code analysis. So the tier 1 would be, you know, anybody could really run a static code analysis tool for the most part, especially the ones that don't require compilation. You can just throw a source code repository or zip file at a tool and it'll spit out some results. That'd be like a tier 1 analyst. But tier 2 to tier 3 analysts would be the ones who have to dive into the actual source code and the alerts and decompose if those are false positives or true positives. And that takes some time, but that's a pretty standard practice, and it requires some knowledge of just, you know, the coding language that's under use. So that could be like C, C++, or something like that. So, but on the binary side, that's similar but different. So a tier 1 we're looking for tools that can help with this tier 1 and tier 2 analysis to help move us to the tier 3 level. So the tier 3 level would be the people who understand disassembled code, assembly language, and things like that. So that's a much harder skill to come by, and not everyone can kind of do that. So you can't take a standard software developer per se and expect them to really understand how to follow assembly code and looking for weaknesses and vulnerabilities in assembly code. So that's kind of what we're talking about. And the one thing with binary analysis, what we found, similar to static code analysis, is there's no one tool, there's no set it, forget it. You can't just throw your binary or throw your press zip file into a tool set and have all the results come out and be pristine. So the set it, forget it, silver bullet doesn't exist, nor do we expect it to. So interpreting the results, like I said, takes software development knowledge, assembly knowledge. You may need architectural specific knowledge, as well as potentially operating system knowledge. So all those requirements for spacecraft binaries, that moves you way up to the tier 3 area where it's very specialized. So we were trying to see if we could find these tier 1 and tier 2 level binary analysis tools to help us out, to help streamline that process. So let's jump right into some of the results. So we're looking at the automated binary analysis that really resembles static code analysis. So to generate insight about the binaries, you typically in the past you analyze the source code, and that's obviously not possible when you don't have the source code. But one of the good things that's occurring in the embedded market with the Internet of Things expansion, car, cybersecurity becoming important, is there's tools coming to market that can help really analyze some of these less traditional x86, 64 binaries and pull out some potential weaknesses and vulnerabilities that we need to dive into. And then you can jump into those with disassemblers like Gidra or IDA to really dive into the details. So what we'd found, probably a few years ago, is most of the COTS tools that were out there that discuss binary analysis were really those component and origin analysis tools, but the market has responded accordingly, which is great. And some of the open source pieces of software that are out there are great, and they're really good tools, but they do require a lot more activation energy to get started. They're not as easy to just jump right in. There's a steep learning curve in some cases. And we explored some of these options just to see what that ramp up was like. So, looking through our survey and looking through all of our tool market studies, we looked into Veracode, and then we basically had to dismiss them as a player in our use case because we're supporting the government and they were a cloud-only solution. So on the COT side, it really came down to Grammatech, who has a binary analysis component to their Code Sonar product line, and then BlackBerry Jarvis as another. And then we singled down to a small list of free and open source tools from Bang, the Rose compiler, Pharos, which is from the Carnegie Mellon Software Engineering Institute, and the CW checker, as well as the Anger framework. So we looked into all these to see if it could help support our use case of static analysis, binary static analysis without the source code, see how that stacked up. So bottom on up front is both BlackBerry and Grammatech's Code Sonar. They were pretty much the only commercial tools that we looked into based on our market research. And we also found some strengths with Jarvis being in the embedded world, which was great because it really fills a gap where something like Code Sonar has pretty decent performance in the x86 area for Windows and Linux binaries, but not really much support on the ARM, PowerPC, and Spark area. So we did look at Code Sonar's beta release. They haven't released full support for PowerPC, and we looked into that, how that performed, and it's still early on for that support level. So bottom line up front, if you have embedded systems, which is what we were really focused on, which are spacecraft binaries, ARM, MIPS, PowerPC, Spark, those type of binaries, Jarvis was pretty much the only solution for that problem set. But it's not a silver bullet either, obviously. So it showed the most promise, and we scanned a bunch of different types of binaries compiled from various types of compilers, RTIMS, VxWorks, hot software for a new bus architecture, firmware from a router, we were successful in detecting some backdoors in some Linux binaries. So when we actually did test some known knowns with Linux, we found some backdoors, which was great. And then we found a buffer overflow exploit in an ARM router firmware. So that was great as well. The FOSS tools showed a little bit less promise, and a lot of those, they're built for purpose, for a single purpose, and they're not, really commercialized entities, which you wouldn't expect. So there are niche areas where these come in handy. The two most promising probably, but require a lot of work with them, are the Anger framework and the Rose compiler. So both of those frameworks are really what they are, provide great capability, but there is a steep learning curve for those and a lot of work on the front end to get them integrated in to analyze your binary, especially if we don't have the source code. So we also looked at Bang and Pharaohs, and nothing really of any subsequent come out of that analysis either. And Pharaohs was really looking for Windows PE binaries was their focus area. So the one FOSS tool that had some promise from the problem we were trying to solve was CW Checker. It was basically low overhead on usage, had some false positives, but did provide some minimal results. So at a minimum, it's worth probably throwing this into the tool set just to see what you get out of, but don't put too much stock in what you get out of it, at least from the work that we were looking into for the things we analyzed. So let's dive into some details on the commercial side, because that showed the most promise for the problem set for us. And we'll look at BlackBerry Jarvis first. So this is a bit of an eye chart, but essentially it was just trying to articulate that, we looked at a bunch of different architectures. ARM, MIPS, PowerPC, Spark are the four that we call out here, and a multitude of different examples. And what to point out on the far right is basically these are the alerts that come out of the analysis, and it's mainly just to show that it was pulling out results, and we'll dive into a few examples moving forward. We also were lucky enough to analyze some quote unquote real flight and ground software. So being in aerospace, we have some unique access to information based on our customer sets. Obviously, we're not going to divulge what these support, but at a high level, we looked at some front-end processor software. We looked at some different flight software binaries or instruments that we were given access to. So long story short is we were successfully able to analyze, small-sat software, pull out some interesting results. We were able to look at PowerPC instrument payloads, flight software binaries, pull out some interesting weaknesses from there, look at some ground system front-end processor software, pull out a lot of interesting information out of those binaries. And one thing that start on the bottom, which is kind of interesting to discuss, is the AVR32 architecture was something that the Jarvis toolset had never seen before. And it was a CubeSat that was launched a couple of years ago, and we had access to the flight software. And we were given access and ran through the toolset Jarvis, and it basically had no support for it. So we worked with the vendor, and within a couple of weeks, they had added that architectural support, and we were able to get some information out, which was good. So that showed some flexibility in the way that toolset was built, that you can add and support that quick. So that was nice. So we found some weaknesses, but let's dive into the next phase. If you find weaknesses, you want to maybe confirm how legitimate they are. Are they exploitable? So in order to do that, we had to really focus on some kind of known tests. So this is where we would go a little bit away from the focus of the research on the embedded side, but we didn't have a multitude of examples of known knowns where they had known weaknesses or backdoors or malware inside the binary that for the embedded architectures that we had access to or could find during the research. So what we did is we leveraged a Linux binary which had a backdoor in it for VSFTP, an old version of VSFTP. And once you run Jarvis against that binary and go through the results, you start diving into the information, and it makes a alert that there's a not sanitized subsystem call there. And if you dive into it, you'll see this basically there's a string right above the BNSH call that it kind of alerted on, that is basically showing that there's some sort of potential backdoor there. Similarly, in this case of the Unreal IRCD, I guess software from years ago, also had a backdoor in it with a system call, a mem copy before system call. So it alerted on that as well. So it was successful in detecting that backdoor as well. So that was interesting. So it was these two old open source projects that had built-in backdoors. It detected it in a matter of seconds, which was great. So what about maybe something a little more embedded? So this is from analyzing some firmware from a router on an ARM processor chip. And this is basically, it discovered a scanf usage, and this was like a wake on LAN issue that the software provided this capability, and it took input. So after running Jarvis against it and doing the analysis and starting to build like a proof of concept exploit, you can basically send this exploit to the web URI, and you can trigger the exploit. So this is just an example of triggering a buffer overflow with this. So the key here is the speed at which, in all three of these examples, is the speed at which this tool set helped us find potential issues that we needed to look into, as opposed to loading this information up into a disassembler and trying to find it ourselves. So that's kind of the benefit thus far to talk about. So what about some flight software? So we also analyzed using the Jarvis tool set with some flight software. And this was an interesting one because we were, we have some in-depth knowledge of NASA's core flight software, which is an open source generic flight software architecture that's been published on GitHub by NASA. It's been used for various spacecraft over the years. And one of the features of CFS that it's built in is this memory manager feature, which essentially allows for permitted arbitrary write to memory commands. And while this is designed to do this, we were wondering if something like Jarvis or the other tool sets could pick up on the fact that they're basically writing arbitrary values directly to memory. And it raised some concerns on unsecure C API calls, and did call out some mem copy functions, but didn't call out the one that we were really looking for it to call out. So that was interesting. So this wasn't necessarily malware. This is just a design flaw that if you only had the binary, you were hoping you could find. And in this case, we didn't, which is a little disappointing, but somewhat expected, honestly. And we also had a flight software image that we used from an old version that had underflow vulnerability in it. And we were seeing if we could find the underflow vulnerability, and it did not find that either. So, we found a couple of backdoors, and we didn't find a few things we were hoping we would find. So what we wanted to do was maybe run some more of the tests, maybe against something of the more known knowns, and that's what we did. So in order to do that, we leveraged the Juliet test suite that's available online, which has essentially a multitude of weaknesses that have been pre-programmed in the software. And we compiled these for embedded architectures and ran them against Jarvis just to see kind of what that would look like. So that, because it's hard to find known bad code, especially for embedded systems, it's we kind of needed to use something that we could grade against, of something of a known test, in addition to the ones we already did. So this is just an example of some known tests we used for Jarvis, and it performed pretty well from our perspective. So you're seeing we spent a lot of time on the Jarvis suite because it showed the most promise for the embedded architecture. So we're not going to have as much data on some of the other tool sets because our focus was the embedded architecture, so the other ones didn't show as much support for that. So it's kind of one-sided from that perspective. But these are the results of that analysis. So now let's jump into Code Sonar and specifically Code Sonar for binary. So Code Sonar from Graham Tech is a product that has been used for many years on the static code analysis side. And then a few years ago, they added in this binary analysis capability, and that's what we're going to look into. So very similar results in some cases for Code Sonar. So this is some interesting visualizations that Grammatech provides that something like Jarvis or the other tools didn't, is this pseudocode and the ability to kind of dive right into the assembly that's there. So Jarvis had the assembly printed out as well, but the ability to kind of click around and maneuver and jump from assembly within this framework was very beneficial. And its decompiler that it has built in and the pseudocode generation is very helpful. You can basically look through pseudocode as opposed to assembly code to figure out kind of what's going on. So that is extremely helpful. So what about the known tests for Code Sonar using that same binary, the VSFTP234? So it flagged something, and it wasn't directly flagging the issue, but it got you close to the issue, and you were able to kind of, if you did thorough analysis, you would have more than likely picked it up. So it's debatable if this is failure or a success, but it puts you in the general vicinity, and you may be able to determine the weakness. So, but it did not alert exactly on the right line of the assembly. So from that perspective, it's probably a failure, but it got you close, and you may have seen it as you were going through the analysis. So how about the same test on the CFS memory manager code? It also raised some warnings with some various calls, and it didn't find the behavior either, which, like I said, it's a design feature of the application, so it probably wouldn't find, but you'd also want to find things that you miss, things that may be considered poor design or poor coding practice. Not saying that this memory manager app is that. It's just something that we were wondering to see if it could pick up on, because if you didn't know that it was designed that way, you may want to know that this application basically gives unfettered access to the memory of the computer. So just throwing that out there. So to summarize some of the usage and coverage that we have, so there's no one stop, one solution for anything. Jarvis had some of the best support for the embedded architectures, and this table can really help show what it looks like. So Jarvis and Code Sonar does have a little bit of the fire and forget mentality. You can at least there's not a lot of pre-work that needs to happen. You can just throw the binary in there, and even Code Sonar on some of these other tools actually have pretty good integration with something like IDAPRO or Ghidra, while others don't. So if that's important to you, that's a factor. They also have varying support for various architectures between PE, ELF, MIPS, ARM, and the rest. So so on the embedded architecture side, like I said, Jarvis provides the most support. If you want some more support for the Windows and Linux side above and beyond, then Code Sonar would be good, as well as augmenting with some open source. But if you have some very skilled talent that has a lot of knowledge on assembly and reverse engineering, you may be able to get some benefit out of the ROSE framework or the Anger framework. So just keep that in mind. But if you're looking for that tier 1 support for somewhat of a fire and forget mentality, Jarvis and Code Sonar definitely appeared to be kind of the best in that area, and it just depends on the architecture. So this chart was kind of put together as a use case, depending on what architecture you're using, what type of binary you have. You could potentially leverage this flowchart to help pick the tool set. So that's kind of the idea, because if you were to come to me and say, hey, I have, not to say you would do this, but if you had some sort of x86 64 binary on the Windows side, and you say, I don't have the source code and I want to analyze it for weaknesses, what would I suggest? I obviously wouldn't suggest Jarvis in that point, because it probably won't find much. Even though that can analyze it, it doesn't really pull a lot of the information out from our testing. I would say maybe use something like Pharos or Code Sonar, depending on what you're looking for. So that's kind of how it's going to have to be. It's going to be a case by case basis, and you're going to have to make that decision based on your use case. So what about once you have these results from a tool like Code Sonar or Jarvis or whatever tool you're using, how do you need to get from kind of point A to point B? How do you know okay, it alerts on this area of the assembly. How do I know what that means? So you may need to bring it up into some sort of disassembler tool set. Now, Sonar did have their own type of disassembler and GUI in there, but Jarvis just gives you a snippet. So you may need to use something like Ghidra, which is just thrown in here mainly just to educate people who may not be aware of it, which most people should be by now, but they do have the support that you need for the embedded architectures. It's free. The community is expanding. People are writing plugins. So Ghidra is becoming widely adopted across various communities. So it's kind of important to know that that exists, and you may need to augment your binary static analysis toolset with something like this to help you dive into the binary a little bit deeper. So here's an example use case from scanning to exploitation. So let's in a comparative analysis. So let's go. So let's go to the side-by-side comparison between the two commercial tools that showed the most promise for us. So Jarvis and Sonar for binary. So we wanted to analyze this VSFTP 234, and we run it through both tool sets, and we want to see what we have. So we find the area of the binary that looks interesting in the memory, and we basically load it up in Ghidra, and then we dive into it a little bit deeper, and we can notice that the software is looking for the characters colon parentheses, and then like a smiley face at a certain memory location. So let's see what that looks like. So let's telnet to that port, and then let's provide the input. And then it starts up a listener on this port 6200, and then you can basically just netcat or tell that to that port, and now you've rooted the device running that software. So this is an example of running the analytics on the binary, finding something that looks interesting, and then trying to actually manually exploit that. And so what's the big deal on that? Because people obviously found that backdoor over at some point in time, so they may have done it through reverse engineering. I'm not sure how it was discovered, but what if you had this tool set in your toolbox at that point in time? So this is the interesting point. So with Jarvis or Sonar, and you were just running these binaries through these tool sets, and then kind of dive it into the details. Speculation, given that Sonar didn't give you the exact line number and just points you in the general direction where there could be an issue, maybe you could have found it within an hour, and then put it, found the issue. If you were in Jarvis, it pointed you directly to the area in the software, and you basically could see within this assembly snippet that Jarvis provided that it was basically, an issue, a backdoor. It was super quick to find. So from 5 minutes to an hour. So what if you were just randomly taking a binary and loading it into a disassembler and manually going through the binary? So that could be weeks to months, depending on how much time you spend and how obvious the actual backdoor is. So it just depends, case by case basis, but that's kind of the magnitude of scale difference. So that would be, how do you go from tier 1 to tier 3 on that pyramid? This is kind of the process, right? You would run these tools, figure out where your issue could be, and then you jump right into if you need to, the disassembler and figure out where your issues are. So what about if we wanted to execute these and we didn't have source code and we wanted to maybe fuzz these things? Is that possible? Like if you have a binary for an embedded spacecraft, could you just run it without having the source code? So there is capability out there to do embedded simulation, but there's a lot of peripherals and things that probably need to be there, especially for a spacecraft, because there's probably things on the bus, there's various cards that need to be there, or it won't run. So it's not as easy as in the Windows world where you can just the software was coded to run on Windows or Linux. It kind of knows that architecture really well and just runs. We don't have that same luxury on the spacecraft, at least yet. So there are some known capabilities out there. There's QEMU, that's really great. It's free and open source. There's RTEMS. If you're running, an RTEMS executable, if you're running the RTEMS real-time operating system, you can use their RTEMS run thing that they've put out. There's a emulator from the Korean Aerospace Research Institute called LACIM, where they have some specialized support, especially for some Spark processors, because they do the Leon 3, Leon 4 in their environment. So there's a pretty good product out there that they have that's free, that you can, it's not open source, but you can get access to it for free using a free license. And then there's the COTS product, CIMIX, that's probably the most robust and has been used for at least 10 years at NASA doing these high fidelity simulations. The problem is it's, you got to have a lot of the information. So is it possible to build a full black box simulation of a spacecraft binary? Not really possible. You know, across the board, it's pretty expensive. So it's teetering on the impossible, but it's not quite impossible. So it's very, very expensive and time consuming if it's super complex spacecraft architecture, which most of our things probably would be. If it's maybe not so unique and there's probably been some reuse of some commercial buses or things that are well known, probably easier to do it. But you know, when you're looking at a spacecraft black box simulation, you know, there's a lot of components to it that you would need to look into. So not fully impossible, because I guess nothing's technically impossible, but it would be extremely expensive to do a black box simulation. And you need to know so much about the software to be able to actually dynamically execute it. So you need to know the architecture, which is somewhat easy to derive, but you need to know all the peripherals and interactions between the backplane and all the different pieces of the spacecraft, which is hard to do. If you have the design documentation, but you just didn't have the flight software, you could probably get there. But if you don't have that, then it's going to be even tougher. And so, you know, you may, to do fuzzing, you may need some sort of full execution environment, and you may not be able to do it. So, and black box fuzzing, like I said, is a little early on in the embedded world, at least from the research that I found. There's some capability out there, but it is rather time consuming to build those harnesses, and especially when you don't know a lot about the binary. So I would say that's not a viable use case unless you have a full execution environment that you can do the fuzzing. So some takeaways and some summaries. So if we're wanting to perform some level of software assurance without source code, and you know, kind of very similar to static code analysis, then we kind of can live on this tiered scale that's here on this page. So long story short is there's no one tool, there's no set it, forget it. There's nothing you can really do from that perspective, but there are tools that can help you get to that point. Interpreting the results is going to take, you know, some specialized knowledge. So if we can curate that specialized knowledge and only use when necessary, and focus on developing these tool sets, these automation pipelines to help out with this, you know, tier 1 and tier 2, that would be very helpful. And you know, we're starting to see some tools emerge to help fuzzing and do black box fuzzing, but they're not quite there yet. And a lot of that focus has been on the x86 and not on the embedded side. So, you know, what's the summary of all this? If you're looking to do software assurance without having access to source code, if you're strictly focused on embedded, then Jarvis is probably your best solution. If you're teetering between the Windows, Linux as well, then you might want to add something like Code Sonar, and then have something like Gidra on hand to do some deep dives. So that's kind of the summary of what the results of this research would be, because we found a lot of good results on various tools, but the embedded side, Jarvis did stand out to us. So that concludes the presentation. I appreciate your time, and contact me if you have any questions, brandon.bailey@aero.org. Thank you so much.